All the protection of CHERI would be moot and pointless if the hardware underneath was not actually doing what we thought it was. Which brings us to Tom Mellon from Oxford, talking about CHERI hardware verification.
Thank you very much. Right, well, thank you. So I'm here to talk about a project that we've been doing on formal hardware verification. That's kind of my background, and my interest, largely my interest in the CHERI world is in that level. And we've been doing a little research project on formal verification of the Chariot IBEX processor, designed by Microsoft. It's an open source processor. And I'm here to just tell you a little bit about the results of that study. We've been having lots of fun with this. So, why, well, Peter alluded to it already, why do formal verification of CHERI processors? This is verifying that the hardware RTL implements the ISA, right? Correctness of the processor is, indispensable foundation for all of the security properties of CHERI. And so, if the hardware is not right, then it's not going to give you this wonderful checking of bounds and so on. And the novelty of the ISA extensions in this case, do mean that for the time being anyway, it's a fairly bug-rich area, right? And there's some innovation in verification that we can do. That's why we like to do research on this. We're delighted that a full specification, one of the bottlenecks in formal hardware verification is getting the specification. They don't always exist, and we're delighted that a full specification is available. We just have to get it into the formal verification tool, right? But specifications are there, and I'll talk a little bit more about that later on. And RISC-V is, a fairly tractable. I mean, it's by no means easy, right, to do. Formal verification is co-NP complete problem, right? So, it's hard, but at least we have half a chance of doing some form of kind of fairly complete verification of a RISC-V processor, and that's what we're aiming for. I don't like doing bounded proofs, but I like to do unbounded full proofs. Okay, so I think you all know about the Chariot IBEX processor, right? This is part of a sort of ongoing. I've got 2 points, so now it's become a program, right? This is sort of ongoing work in verifying increasingly complex CHERI processors, starting with the RISC-V flute, which Dapeng over there did, and then this Chariot IBEX. We're interested in doing further processors in the future. We've not done anything with out-of-order execution or anything like that yet, and that'll be fun. And so we started, and Microsoft very kindly made the Chariot IBEX processor available to us, and this is an adaptation of the IBEX processor with the additions of CHERI instructions, and we were able to start work on that in Oxford. And as I said, it comes with this sales specification. Okay, so what are our principles here? Well, we're aiming for full coverage of the entire ISA, right? Everything, not just a few properties, but everything. We want to cover both CHERI extensions and RISC-V. We've got a sort of side interest in RISC-V verification in general, right? We want to do no FV-driven modifications to the sales specification, although we're sorely tempted in one case to do that, which I might have time to talk about. Complete proofs, as I said, and as end-to-end as possible. So in hardware verification, end-to-end verification means taking the data path and saying, an instruction comes in and the right updates to architectural state happen, right? And that's in contrast to component-based verification, where you'll pull out the divider, or you'll pull out the multiplier, or you'll pull out the branch predictor or something, and you'll verify those components. We're trying to do this end-to-end thing. And sort of slightly unusually, we have the leisure time in academia to make regression as fast as possible. And so we want our proofs to run fast, right? And that takes a work. Okay. Oops, that's not right there. Okay, so what are our outcomes? Well, we found numerous bugs. I'll tell you about those. Outcome is higher confidence in the correctness and security guarantees offered by CHERI, but there's no fully verified 100% always going to work device anywhere, right? So just don't imagine that this we get more confidence, but not sure. There's nothing sure. We're developing new methodology and tools, and we will be releasing this full verification as an open source example with a permissive license for anybody who wants to use it. in due course. Eventually, I'd like to push this further into some kind of configurable proof kit covering more of RISC-V extensions. That's a bit difficult to do. And maybe some kind of full integration of hopefully SAIL into EDA, or at least EDA would pick this up so that this can become commonplace. Right. Okay, so I'm going to talk a little bit about the SAIL to Verilog compilers. So we have a specification in SAIL. Formal verification tools do not read SAIL, right? Yet. Okay, I mean, commercial formal verification tools do not read SAIL. There's this amazingly rich SAIL ecosystem here with many elements, and Alistair Armstrong is probably in the room somewhere. There he is. Very kindly collaborated with this effort and built a prototype SAIL to Verilog compiler. Okay, and he did that by sort of tapping into the SMT, this satisfiability modular theories flow in the SAIL ecosystem, and diverted the representation at a certain point of that flow into Verilog syntax. Okay, so we've now got a Verilog. This is the hardware description language for chip designs. Got a Verilog description of the chip, and we can then plug that into a commercial state-of-the-art formal verification tool. The one we're using is Jasper from Cadence, and it can eat this Verilog and use it as a reference model against which to check the RTL. Okay, so that's the idea, and this really overcomes an absolutely huge barrier to productivity that DAPing in particular experienced in the last verification, where if you have to manually write the specifications, then you're essentially typing out a SAIL spec sized piece of specification again in another language, and that's error prone and takes a lot of time. So this is really a step change in capability for this work. Okay, just a little bit about the specification. So we get this lump of Verilog coming out. It's purely combinational, state in, state out, just a function from input to output, no state in there. The elaborated size is quite large, so it takes about 20 minutes to load the entire specification into Jasper. And everything's a bit slow if it's used, but we're not worried about that. This is a prototype, and this can be overcome in the future. We've got some hackish tools now to essentially chop out instructions you're not interested in working on that afternoon, right? To load it quicker. But eventually, when you regress the proof, you want to load the whole thing. We can't realistically instantiate the specification several times in the system has been instantiated once. This could be improved with some better abstraction techniques, or my favorite formal verification method, symbolic trajectory evaluation. I think is going to be really a killer in this domain. So I'm very interested to work on that at some point. Yeah, and as I mentioned, for development, we just carve out the piece we want that time. So here's the Chariot pipeline. It's pretty simple processor, right? No branch predictor. There's no exception handling in the diagram here, but we did do the exception handling. Misaligned memory accesses are allowed. The number of registers is quite reasonably small. The pipeline can stall waiting for memory. When the pipeline sends a memory request off, it can stumble on for a few cycles, but at that point it then has to stall until memory comes back. And that's not fun for formal. Okay, so that's the pipeline. So how do we plug the SAIL specification in? Well, we've got this lump of Verilog, and we like to be end to end, but that doesn't mean instruction coming in, before instruction fetch and the other end being the write back stage. It first of all makes sense to slice off the instruction fetch part and verify that separately. Instruction fetch is basically a FIFO. FIFOs are not that much fun to do formal hardware verification on. I'm just talking about the capacity of the tools, but you can do it, right? So it really makes sense to start after instruction fetch. We have verified instruction fetch as a separate unit. But the other end of the pipeline is not that well defined, because an architectural state can be updated all over the pipeline. So it's not like everything waits to the write back stage and then bang, hits all the registers, okay? Bits of state get updated in data dependent way sometimes. and exceptions and so on. So the other end is not that well defined. You have to sort of work that out. So in common with other efforts, like Alistair Reid's efforts at ARM and so on, we've installed a pipeline follower so essentially the specification grabs the instruction that comes out of instruction fetch at the same time as the pipeline grabs it. Specification computes the expected result, and then the expected result accompanies the instruction through the pipeline, okay, and is available to be compared to what the pipeline's got when it touches architectural state. That's the pipeline follower idea, and that accompanying has to be in sync with things like pipeline stalls and so on. Okay, so the pipeline in some sense controls the pipeline follower. That's why it's a follower, but it just basically caches the expected answer until it's needed for comparison. And so it kind of works like this. Spec calculates the thing, the expected result, and then we kind of pipeline it along and do comparisons at the points where comparisons are needed. So that's the pipeline follower. It's a little bit complicated to figure out how to install this. I've got a plan in the future to do this automatically. Look, we know the latency of all the operations through the hardware, right? So we sort of know when architectural state will be touched. So we really ought to be able to get a sales specification out in Verilog and just have it auto plugged in, right? He says, right? Subject to funding, right? Okay. Yeah, and as I said, we do the instruction fetch separate, and that does make sense. It just doesn't make sense to do both of those things. You do a cut there. Okay, so one of the interesting things about this is that decompression is expensive operation. It's free. It seems pretty liberally used in the sale, right? And seems a bit free there, right? But in hardware, it's costs you time to decompress. There's some variable length shifts. There's some arithmetic that happens and so on. So for efficiency, there's a sort of shadow copy of some information from the compressed instructions that's carried around along with the compressed capabilities. That's carried around. These top core and base core fields are cached in the IBEX processor. And so now we've got two copies of the same information, right? And do they correspond? Okay. So you've got to prove, it's hopeless to prove anything about this unless you can establish that those two things keep in sync throughout the processor. So that you've got to establish a global data type invariant. Fortunately, we teach about data type invariants in the first term of Oxford University, second term at Oxford University, so we know how to do this, right? And our students know how to do this. So we have to establish a global data type invariant here. So that's not particularly easy to do. If you just type your invariant up and give it to the model checker and say, please prove this, it will just go to lunch and not come back, right? So it's just not tractable to prove this data invariant. So how do we do that? Well, I'm an old theorem proving veteran from deductive theorem proving days, and I would of course do a proof decomposition into subproofs and then compose those to get the proof. And the right kind of subproof here is an induction. Okay, so that's exactly what we did with the model checker. We analyze the flow of capabilities through the various things that consume and produce capabilities, all right? And then for each one, prove a little step case of an induction that shows that the well-formedness is maintained by the system. Okay, so here's an example for the register file. This kind of logic here, you only have to look at the bottom things there. They sort of say that if the first property, DTI int RF, says if the register file state is okay and the input is okay, then in the next state of the register file will be okay. Where okay means that the correct correspondence between compressed and uncompressed cached stuff is maintained. And then there's another one that says if the state of the register file is okay, then the outputs will be okay. Okay, and note, right? And from that you can deduce that the register file state is always okay. And from properties like this all over the thing, you can infer right? Just like you would in a deductive theorem prover, that the assertion is true globally across the processor for all time. Okay, so that's the data type invariant, and yeah, if you don't prove that, you get lots of false negatives. It essentially constrains the state space to something that's well behaved, and so this is something I think probably would have to happen in any serious microarchitecture for a CHERI processor. Right. Little word about memory. We'd love to verify memory under an unbounded liveness assumption about the memory. So we'd like to have an assumption that says, if a memory request goes out to memory, eventually the memory responds. And those of you who did linear time temporal logic, you know, the eventually operator, right? It will come in the future. That's a liveness assumption. And liveness doesn't play well with any serious formal verification tools. It's hard to do. You can do it with I've forgotten the name of the engine, but it's a little bit difficult to handle. So at the moment, we just assume that we get memory coming back within 10 clock cycles, and the maximum I think the processor can stall is probably maximum the processor can go beyond a memory request, and before stalling would be about 2 or 3 cycles, just architecturally, right? So we kind of know that this is okay, right? But of course, when I'm thinking of hardware verification, I'm always thinking of some kind of evil gremlin who comes in late at night and types in a small state machine in the corner of my RTL that counts to 100, and then 100 cycles, and then messes things up, right? And how do I know that that's not in there, right? And so we don't, because we haven't done this unbounded proof. I think we probably can do the unbounded proof now because of our regression speed. This gives us a hope that we ought to be able to. We have enough stuff in there to get to do unbounded proof, right? Okay, so we're assuming a bounded memory response time for the moment, right? That's interesting. Oh yeah, so yeah, I'll just say another thing about memory. It's not on the slides, but we had a debate with the Microsoft team a little bit about whether capabilities coming in from memory had to have some kind of well-formedness assumption, right? Or whether they're just going to be okay when they come from memory. And it turns out we do have to have a well-formedness assumption because of some obscure thing that Louis Emile understands, but I'll have to remind myself about to tell you about. So we did develop a constraint that we assume about the capabilities coming in from memory. And so how do we know that's right? We actually include that assumption in the data type invariant. We augmented the data type invariant with that assumption and prove that it holds throughout the processor. So in other words, we prove that the processor never produces the kind of ill-formed data that we assume never comes from memory. So that gives us some kind of confidence about that's a reasonable assumption to make, right? So we've got that assumption in there. This created quite a bit of conversation between us and the Microsoft people. Okay, so we've got an absolutely glorious harvest of bugs here. We get paid when we find bugs, right? We don't get paid actually at all, but we get rewarded morally when we find bugs. So approximately 25 bugs found and reported, and we report them all to the you can see them all in the Chariot Ibex Git repo and discussion of them and so on. At least 4 of the bugs break the sacred monotonicity property of CHERI, which is that capabilities never get expanded by anything, okay, or permissions don't get gained by anything. They only can be reduced or kept the same. The 4 of the bugs do break monotonicity. At least 1 bug has a pretty fanciful but not impossible software exploit, which was also reported. So we loved that. That was fantastic. And by the way, the maturity of the RTL I think was fairly low, right? So just because there's all these bugs, please don't imagine that this is not a high quality design. It's a high quality design, but there's always going to be bugs in design. So it's not unusual to find bugs, especially when formal is applied at a fairly early stage. Okay, we found a lot of simple blunder type bugs that would have been found with simulation. Some of the bugs we found, I cannot believe that they would have been found with simulation. Yeah, I'm getting a affirmation of that over there. Yeah, and as I said, formal prompted discussion about what's a valid capability coming in from memory. So these are all reported on the thing, and I think they're either fixed or in the process of being fixed. So that's good for us, right? Good for the community. So progress to date. So I'm very happy. As of last week, we have all the CHERI extensions instructions. So we're verifying instruction by instruction, right? So each instruction has to do the right thing, and all the CHERI extension instructions are verified fully with fully conclusive, unbounded proofs. So that's about the best it can get, right? So including general purpose registers and the memory proofs are under bounded assumption, as mentioned, including the RISC-V compressed variants, which is the one place we'd like to rewrite the spec a little bit. I can talk to you at the break about that, but we got some hacky solution for that works. Program counter fetching and exceptions, instruction fetch correctness, and all kinds of things, and IRQ handling. They've all been covered. So there's a handful of to-dos here, some shifts, M-type. So the M-type instructions, I think that's going to be me proving that, because that's data path, and that's what I do, right? So I'm dying to get my hands on that divider. A few other things. CSRs are a little bit fiddly because there's so many of them, right? But we're doing there's a CSR instruction, so we're just verifying that instruction, and you get a violation. And the reason we're getting, and we go, oh, what's the problem? And the reason we're getting violations, we didn't drive that part of the specification with the information needed to get the correct expected answer out. So we have to beef up our specification installation. It's a long cycle to do that. WFI, it's kind of unclear how that's going to be, how hard that's going to be. Fences, we have to figure out what to say about them. The other thing we didn't cover was we didn't verify that in between instructions, the processor doesn't go haywire and change stuff, right? And actually, there was one bug reported on the repo for CHERITech of that kind, which we didn't find, right? We want to cover that as well, so we can check that's done, and that should lead to some kind of proof of trace for those process algebra people. I know you are back there. We'd like to prove some kind of trace equivalence. So in other words, take the sale and take the processor, start them in the current state, and let them run with the same inputs, the same memory forever, and they will always course. Their state updates to memory will always be identical, so their actions will be identical, and that would be. I think we would then believe that we've proved everything, right? If we could do that, and not simulation on a particular code sequence, but on whatever the code sequence is, right? That would be great. That's a co-induction. We've forced the model checkers to do induction somehow. So how we're going to do co-induction, I'm not sure. And of course, the next thing to do is to verify the operating system and the other layers of the stack on top of this. We had a little bit of experience with assembly language code verification. It wasn't a happy experience, right? Yet. So we need to do better. And we've got all kinds of potential compiler and tool improvements. We're talking to Alistair about that and Peter. DAG inlining. So it's too big, right? So some kind of DAG inlining for the thing. Stop-outs are the Jasper term for freeing abstraction. So some generated stops. So these abstractions are how you prune kind of parts of the spec that aren't relevant. I think I can do that automatically. I think I've got interesting ways of doing that automatically. It would come for free if we used symbolic trajectory evaluation, basically. Some compressed instruction splitting. This is the place we'd like to rewrite the sale, but we're not going to do that, right? There's a tool for that. And I'm very interested in better debuggability. So the sale is ugly and big and bears no the Verilog, sorry, it comes from the sale is ugly and big and well munged and not that well understandable. So when you get a bug, right, or you get a violation, you have to debug it somehow. I think a very simple first step to that would be to get a trace out of the model checking tool and convert it into a sale emulator or whatever you call it, input so that you could run the sale on that case and see what happens. But we'd like to have back annotation that works really well. And dealing with RISC-V configurability in general is a much longer term project. So there's the team, Louis-Emile, lead formal verification engineer, probably responsible for like 90% or more of the actual progress on this verification. Is absolutely brilliant job. Ray Lin took this on as a third-year undergraduate project initially, and then Louis-Emile extended, and we had 2 other people working last summer from here in Cambridge who also chipped in on this. And Alistair did not give me his photograph, so you're not on the slide. Right. But next time. Right. Thank you.
That's great. Thank you. We have -1 minute for one question.
Including the debug extension. I don't know what the debug. So the question was, can we verify including the debug extension? And I don't know what that is. So the answer is maybe. I'm sorry, I don't know what that. Maybe you can explain it to me at coffee, and we can think about it.
Simon, if it's quick.
I'm just wondering how tractable you think it might be to verify the second. Obviously, you're verifying against those.
Yeah. So the question was, how can we verify the compilation from sale to Verilog? So I would simply hit that with thousands of test vectors, right? And do that in simulation. I mean, it's not straightforward to see how to do that. We played around in Dapeng's time. We played around a little bit with the C generated from sale, but it's not suitable really for verification because it's an emulator, right? And it's got all this kind of big int stuff, and so yeah, I don't really see anything formal happening there. But you could just subject it to a huge ton of test vectors for a long time, and yeah, and just check it that way.
Okay, thank you very much.
So, thank you.